Okay, so we can start with Professor Amir, the second lecture. Yeah, thanks, Amir.
Hello. Okay, that was my last slide yesterday. So we were discussing these devices, superconducting devices, and in any sort of picture that I try to use, we always have some sort of dissipation in the system, right? I wrote the equation for the flux inside the ring, inside the superconducting ring, and then that was a sort of dissipative equation of motion. And basically, we have a paradigm for our systems. In all of them, they obey this sort of equation of motion. Either the split ring or Josephson junction, they obey exactly this sort of equation. And that's the equation that we have of a particle in the viscous fluid. And that's basically Q is the coordinate of the particle, and then we have a sort of external potential. So the derivative of that is so it's a force due to this potential. And then there is the fluctuating force, which is zero on the average, and it has this sort of white noise dependence. So that's this sort of system that we play with. We always have, a sort of RLC circuit, for instance, is a system that obeys this sort of equation of motion too. And for the superconducting devices, we have exactly something like that. And the question is, what about quantum mechanics? How can we deal with these sort of equations in quantum mechanics? We know that we cannot find a sort of Lagrangian from which we can derive this sort of equation unless we make maybe different strange hypotheses. And so the thing is that the prescription here is to couple the system we're interested in with the environment. And we always have this sort of picture there. That is the system that we are playing with coupled to an environment. And that's the most general thing one can have. And that's exactly what we're going to apply. And then there is an interaction between the system of interest and the environment. And so, when we're playing with that, this is the full dynamic in the quantum mechanics. And so fine. And in order to do that, we suppose we have a very general mixture in our system. So we have the full wave function, the full state of the whole universe, particle and environment. And that's the sort of classical probability distribution for whatever is described in this side here. And that's the time evolution of the system. And this guy here is the full Hamiltonian. So time evolving, all the universe, all this the composite system and environment. And then, if I want to focus on some sort of variables of the system only, for instance, the coordinate and momentum, what we have to do is to take this prescription here, that's the trace over this rho of t times the operator O. And of course, since this guy here does not depend on the coordinates of the environment, we can only say that we can trace first the environmental coordinates, and then we end up with something like rho twiddle, and that's rho twiddle is the reduced density operator of the system. Mind you, that's exactly something like I presented yesterday. But yesterday I was talking about the reduced density operator for one single particle in an environment of identical particles. Now we have something distinguishable. So that's the guy that can really follow these observables, Q and B, for the system of interest. And then that's what we need to do to compute this sort of reduced density operator of the system only at any time. And so let me try to explain these long expressions. So all I'm doing here is to find the coordinate representation of this reduced density operator of the whole thing. And And this is K. K is just the time evolution operator. That's the unitary operator, with H being the full Hamiltonian. Right? And then I have the representation for the system X, X dot, X dash, and R dash for the coordinates of the environment, whatever they are. They can be a very complex coordinates, I don't care. It belongs to the environment, right? So then we will try to make it simpler later. And but then we have this sort of time evolution here. Now this guy here is making the time evolution of the cat. We have the bra here, and the cat and the bra. So we make the time evolution of this cat and time evolution of the bra, which is the time reversed of this side, cat side. And so if we do that, what we have is this position representation of the unitary evolution operator and its complex conjugate. So that's the for the cat and for the bra. And we now we make the sort of position representation for these initials test operator for the composite system. Right? So that's what we have. And let me just remind you that this sort of operator here, we have a path integral representation of that. That depends on the action. And so I can describe my system in terms of the Lagrangians of the system, of interaction and the environment, and I can write the full action for that, and we make this functional integral in n plus 1 dimensional space. Right? Okay, it's only a representation for our system. And mind you, it will be very useful, very shortly, to use this sort of representation. Now, let me make some sort of hypothesis about the initial condition. I'll say that the initial condition is such that I can split something which belongs to the system and of the environment only. I can say, for instance, that I prepare a wave packet just reaching the system, and that's the equilibrium density operator for the environment only. And if I do that, I can put it back there, and we can write the reduced density operator as this sort of double convolution. Mind you, this guy here is the reduced density operator of the system only. Right? And this guy here, I'm going to call that a super propagator, because it's propagating the reduced density operator. Right? It's not only the propagator of a wave function, but single pure state. It's the wave function is the propagator for the full density operator. So, and then this guy here, if I just put it back there, this condition up there, we can show that this J here is super propagator is given by the evolution. Now that's the thing here. That's important to see what happens here. That we make the time evolution of the full universe, and that's the complex conjugate of that. And we have to trace over these final configurations of the environment and make this double average for the initial operator of the environment. So there is a prescription to write this sort of super propagator. But the point is that if I just plug this sort of thing in here, we'll have problems trying to separate what belongs to the system and what belongs to the environment due to the non-commutativity of the operators. So what I can do is the following. Then, if I just jump from this sort of description to this one, I can make this sort of separation. Let's see how it happens shortly. Okay, so actually here's this expression here. If I just say that I use the path integral representation for the time evolution operator, we can write this super propagator as the double path integral. of these paths of the particle only, and that's the action of the particle of interest, and that's the conjugate particle of that. And then there is this functional, which we call the influence functional. This guy couples the two histories, right, for the system. And one for the time evolution of the cat, and the other one for the time evolution of the frog. And that's what happens. And then we can write this guy here in terms of this double integral for the initial density operator of the environment. And now look at these double integrals here, these double functional integrals. One of them refers to the time evolution of the environment in the presence of a particle, right? And so what I have to do is to perform, imagine that we have the environment and then I move the particle in the environment. So I can say that this motion acts like an external force to the environment. And the environment will time evolve due to this external influence of the system of interest. So I do that for these two operators here, for this time evolution of the environment in the presence of x, time evolution of the environment in the presence of y. And so that's just two time evolutions. And then I'll couple them through these integrals here, because these guys, we always start in r dash, going to r, q dash, going to r, and make these double integrals with this equilibrium density operator for the environment. And so this way to write the problem is nice because I can split into something that refers only to the particle of interest, and something that refers to the environment, but all the influence. This guy is a double function, it's a function of these two variables, but it contains all the information of the environment. So there's a sort of feedback. I move the particle in the environment, and the environment responds back into the particle. So that's what happens here. And this sort of behavior is coupled by this influence. So this guy couples these two histories of the particle. One for the time evolution of the cat, one for the time evolution of the frog. And fine. And once there is no coupling, this influence functional is one, and then I can split these two time evolutions. In time evolution, forward in time, you get one backward in time, with no environment at all. So that's fine. And that's a nice way to write it, although it's not very popular. I admit people don't like to play with technical, but it's very useful in this case. Then, and what about S? S is just the action of the particle only, the interaction action, and the environment action. So, okay, now, let me take a sort of minimal model for my environment. So I'm saying that it's a very general environment, and I have two choices here. Either, remember, I was thinking about superconducting devices. I told you that this particular term comes from normal currents and things like that. So the environment itself might be quite complicated in this case. We don't really know. Actually, we know, but we have to have details of the junction and things like that to know exactly how to write a microscopic model for the environment. In this case here, what I'm going to do is to apply something else, not the realistic model for the of HS or the interaction with the environment, but I will say that I will take a very simple model, not for HS, sorry, it's HR here, right? And I will take a very simple model for the environment, and I will assume that this model is such that in the classical limit it will reproduce the Legendre equation, namely the paradigm I showed you on the first slide. Okay, so I will take the following. That's the Lagrangian of the system. I will take an interaction Lagrangian, which is a bilinear coupling of the coordinates of the particles of the environment and my coordinate of interest. And this guy here turns out to be a set of non-interacting harmonic oscillators, right? Pure model. I can tell you why you can choose this model later on. But let's take that as a good example, a good model, and there is a sort of counter term that will be very useful in the future. I will tell you why later. And actually, I will tell you why we need this counter term. And so that's the sort of model we're going to apply. And so, what do we do here? We know exactly what the environment is. And we can easily write the equation of motion for the particle of interest and for the coordinates of the environment. These are the two n+1 equations of motion, right? N for the environment and 1 for the particle of interest. And now I can take the Laplace transform of the kth equation of motion here. That's the Laplace equation that we have. And now, what I'm going to do is to plug it back into the first equation in this UK here, but then I have to take the inverse Laplace transform to put it back there. So I have an effective equation of motion here that reads something like that. You know, it's this inertia term, the force, and now this term here that comes from this part here of the environment. So it's a sort of a feedback of the particle on itself, right? And through the environment. And these guys here, they depend on the initial condition of the harmonic oscillators, as we can see here from this second equation. So we have one expression that is related to Q2 twiddle itself, which is the Laplace transform of the first one, and actually, it's okay. And the second one, which depends on these initial conditions. And we can guess that it would be very nice if we could write this sort of thing here as eta q dot, and this guy here as the fluctuating force, right? So it will be very appropriate for our needs. And let's see what happens here. That term, the second one, can be written as a derivative of this sort of expression. And this is exactly the Laplace transform of a cosine. So this guy here is the Laplace transform of a convolution product. And that's the convolution product. So our term actually can be written as a time derivative of something like this. And I can also use for the environment the following. I will say that at initial time, all my oscillators, they are in thermal equilibrium in such a way that we can use the partition theorem to write these expressions. So these are the average of the oscillators, which are, I call that Q bar Q, and average 0 here. And now we have something that can reproduce the partition theorem. So our oscillators are in equilibrium in the presence of the particle immersed in the system. So that's what it is. And then, now another thing, if we look back, we see that we still have something to play with. It's a summation over all these scales here. In order to perform these summations, I will define something which is called spectral function, and the spectral function is this nice combination of coupling constants and masses and frequencies of the oscillators. And if we do that, and moreover, if we model that in this way, we say that it's a prefactor and a power law for the frequency. If we have low frequencies, and for high frequencies, we have zero spectral function. So we always define the spectral function only for frequencies less than the cutoff frequency, which is a very high frequency. Now, if we say that S is equal to 1, and this A is given by eta, we have exactly what I need. That's the Langevin equation, and the average is 0, and if I compute that using this equation theorem, I can write that as a white noise. So my equation, so that's a good system. Why? Because all these realistic systems I was playing with, they obey the Langevin equation down to very, very low temperatures. So I can rely on something like that to see, okay, if I try to address very general quantum mechanical questions about my system, I have to use this sort of, I can use this sort of model. And I can reproduce the Langevin equation, so all I have to do is to play with that awful double path integral with the influence functional and so on. But then I have something being solved by brute force. There is no sort of approximation. It's quite general. If you take it as a model, then you can ask me why is that. So I can just anticipate the following. This model is always valid if I can assume that the environment is being acted by the external particle in such a way that it obeys linear response theory. Every time I can use a linear response theory for the environment, done, I can use this sort of model oscillators. So it's quite general. It's much more general than we can initially think. But okay, let's go on, and I can also, instead of using this S equals 1, which we call ohmic dissipation, I can use something which is called in the literature subohmic, when S is between 0 and 1, and for S greater than 1 is the superohmic case. Mind you, for S equals 3, we can reproduce the Abraham-Lorentz equation, which is the equation for the radiation debris. So we can do a lot with this very naive model. We can play with the Langevin equation, Abraham-Lorentz. We can do a lot. Now, okay, fine. So, and now we another thing is the fact that we can write the Lagrangian for the whole system in a different way. Instead of coupling QQ, QQK, I can couple this thing with the different coupling constants and coordinate to velocity of the oscillator. I can do that. And in this way, we have something like the, say, linear vector potential times the velocity, and the external particle will be a sort of mode of the electromagnetic field and coupled to the charge oscillators. So that's something that we can do. And if we start with this Lagrangian formulation, go to the Hamiltonian formulation, and perform appropriate canonical transformations, we end up exactly with the same model as before. It's a system coupled through bilinear coupling, coordinate, and with the counter term. Notice, in this place here, there is no counter term. Right? It's completely a translation invariant in this case. And this translation invariance will become clear in the next slide. For instance, I take another way to write the same model. I make this sort of transformation here for the original model, and I can transform that, the original one, counter term and coordinate, into something like this. With these new masses, mu k, and this new spectral function that comes about because of these transformations. And look at this. That's the same sort of thing. P squared plus V, and the oscillators. But now, the oscillators are sitting on the particle itself. Right? It's not something like a external particle coupled to springs attached to a wall. No, it's not that. It's something else. It's something like this, for instance. Right? Of course, we can see that it's completely translation invariant when we have this V equals 0 here, right? So if for a free particle, this guy is translationally invariant. You see from this picture here, all my springs are attached to the particle itself. And that's the non-linear whatever spring that I have. So it can be as general as I want. Right? So the thing is that this system turns out to be manifestly translation invariant for no potential. And so that's what we have. That's what we have. We have a very large particle of harmonic modes coupled to the particle of interest. And then we move that. Then you can ask me, come on, where's the dissipation coming from? Because you know, this guy's translation invariant. Remember that if I apply a force there, the force is applied in the center of mass. If I apply a force, for instance, in this particle, actually it's applied to the center of mass of the system. But now I have an infinite system. So the velocity of the whole thing is very small, zero. So I'm transferring all this momentum to this blue particle. And I start to excite modes here. So that's why we have the spatial. Can you hear me? I'm sorry, sometimes I don't put my neck close to my mouth. Anyway, so that's the system that we have. And again, see, I say that every time we have a very complex environment, and I can use linear response theory to deal with it, I can replace it by linear harmonic oscillators. And at least from this you can say that, well, suppose all my environment is here, but very close to the particle itself. I can say that locally, the particle will always obey this sort of thing. And actually it has to be like that. Because if I move the particle here, there, it must be the same. There is no privileged position for the environment. Now, so let's go back to that horrible thing. Right? It's I have to compute actions, but now I have to compute actions of forced harmonic oscillators. And you can do that classical, right? So what we have to do, the advantage here is to say that I can always play with these guys, and what I need to do here is to compute the classical action and exponentiate it. And that's force of harmonic oscillators. And the action of the case of oscillator is given by the solution here. Right? And that's the initial, the final position. You find it in any quantum mechanics book. That's the, well, actually, classical mechanics book. That's purely classical. I will exponentiate that. I'll put it back there, and then I'll make this average. And the average with what? With this density operator of harmonic oscillators in equilibrium. So that was my initial choice when I used the partition theorem. But now I'm generalizing that to the extreme quantum mechanical case, a very general case. Mine, so far, no approximation. Once I believe in the model, it's exact, right? And then, my super propagator is then something like this. The free ones, and this guy here, he takes place because we have the counter term, but will disappear next, because you know there is some terms coming from this double integral that will cancel the counter term contribution there. And then there is a real part here. And we know these functions which are given by these expressions. So everything's exactly here. And then my super propagator is the double path integral of something which is the action of the particle of interest for x, for y. And then we have another contribution. And this guy here, it comes in this way, x dash dot y dot x. Always quadratic. Always quadratic. Right? So that's why it's useful, because I can perform these integrals exactly. Right? And again, And the last term is something like this, because mind you, I'm using this spectral function, right? So I replace all my summations over this case by the integral over the j of omega, that spectral function. And that allows me to write in the end of the day something like this. So I'm ready to apply that. So just tell me what sort of system I have here, because all the influence of the environment is already there. No more environment. It's just a sort of coupled set of histories of forward and backward in time. Mind you, that's exactly what happens in the Caldeira formulation of non-equilibrium systems. And we have exactly the same. Caldeira has a sort of path going forward and backward in time. That's exactly what we have. Time evolution forward and backward in time. And coupled through the influence function. Okay. Another kind of problem that shows up very often is the following. Is the problems that we play with the full Hamiltonian of the whole universe in equilibrium. And then if we do that, we can define this operator with the parameter beta. I'm talking about something in equilibrium now. Beforehand, we are talking about real time evolution. Now we're talking about equilibrium, right? So that's the equilibrium of a particle in a medium. So the whole thing is in thermal equilibrium. And if we do that, again, we can use this double path integral representation for this guy here. Once I regard this beta as IT divided by h bar. So that's a sort of a measuring time version of the simple propagator for the whole universe. And then what we have is a sort of Euclidean action where I replace all my times by imaginary time. Remember that imaginary time is related to beta now. And then we can perform the sort of things here. The only difference is that now I do not have forward and backward in time. All I'm saying is that I'm using only imaginary time description for the operator. Now, when you do that, we have a final form, which is the path integral over this coordinate in imaginary time and an effective action. And this effective action is given by this expression. And, you know, if I take this alpha here, it's just a replacement of all this summation by the integral over j of omega. And for ohmic dissipation, which is my main goal here, is given by that. So it's 1 tau minus tau dash square in here. So that's the effective action we have to play with if we want to address systems in thermal equilibrium. Good. Now let's start with some applications. What about the damped harmonic oscillator in real time? I start with a Gaussian wave function and I give it a kick momentum with a width sigma, and I plug it there in the double path integral with the influence function also one, but I know exactly what it is, and I can perform that integration. And the Gaussian, the diagonal term of that Gaussian, that's the time evolution of the initial condition. We have exactly another Gaussian, but of course, you know, my initial position is a Gaussian, and my double path integral is quadratic. So you have to end up with a Gaussian. Nothing else is practicable there. And and you see that the center of the wave packet here obeys exactly what? The classical equation of motion of a damped harmonic oscillator. Right? And the width in equilibrium in infinite time, where gamma is eta by 2m, and this omega is omega naught minus gamma 2 minus gamma square, exactly as in the classical regime. So, okay, and what about the width? The width at equilibrium is given by this expression. But this expression here turns out to be that guy here is the imaginary part of the response of a damped harmonic oscillator. So that's nothing but the fluctuation dissipation theory. At a full form, no approximation of high temperature, low temperature. That's the most general there is. That's the fluctuation dissipation theorem. And then you can just play with that and say that the width will change in this dimension as damping, which is gamma divided by omega naught. And you see that these are the expressions for underdamped or overdamped oscillators. And the thing is, in equilibrium, regardless of the limit I'm going to use for underdamped or overdamped, the width of the oscillator will always tend to shrink. And what's the meaning of that? The meaning of that is become more classical. 0-point fluctuations in position are becoming narrower. So it's becoming more classical. As I have damped system, it will tend to be more classical. That's the picture that we can draw from this result here. Now another one, which is this, that's quite interesting. I just create the initial condition of one particle, but this one particle is not centered, and is centered, is delocalized. We can create that quantum mechanically. I'll give you a couple of examples. You can create that quantum mechanically. An ion, for instance, in a magnetic optical trap can be, we can create that in sort of superposition here and there. That's a single ion. And so, if we do that, see, we have two displaced Gaussians. When you do that, what I have to do is, okay, I make the time evolution of this reducedness operator. There is the one related to the wave packet 1, to the wave packet 2, and then there's a sort of interference between these two wave packets. And so, the time evolution of this system will be something like this. This guy will be one packet within sort of damped motion. The other one can be something close to the origin, for instance, or another damped motion. And in the end, what we have here is that this interference term is still something like intensity 1, intensity 2, and then we have this interference pattern and one extra time dependence. And this time dependence is the time dependence of the destruction of interference between these two wave packets. And then, if we do that, we'll see that this guy is given by this. We know that gamma is the time that the wave packet takes to relax to equilibrium, right? And now I ask, what's the relation of this big gamma, which is the time related to destruction of interference, with the small gamma? And so we have that, for instance, for high temperatures and for low temperatures. For low temperatures, it's easier to see that this guy is really n times, where n can be very large gamma, or n times omega naught squared by 2 gamma for extremely overdamped systems. And then there is there's also an influence of temperature in these two cases for temperatures such that 8 each bar omega naught is much less than 280. And then this n is basically the measure of the distance between these two centers of the packets in unities of their width. Right? And that turns out to be the number, the average number of quantum of energy in my initial position. Right? So then we see that if we prepare the system with two packets very far apart from one another, what happens is that even before they overlap for the first time there will be no interference left. So we prepare that in such a way that I can cluster and distinguish the two wave packets. They become clustered in a very, very short time interval. So that's clear example of destruction of interference or decoherence, if you will. Good. Then that's the picture that we have. Two wave packets, the interference. Now, as they start to approach one another, I start to destroy this picture. Even before they cross for the first time, I repeat. No more interference left. And so, that's what it is. And we have a couple of examples. And that was measured, right, by the group Serge in Paris with coherent states. They prepared a sort of X state of two coherent states, alpha minus alpha, in a cavity, and then they can see the destruction of interference in a very short time scale, depending on this distance to alpha between this distance, right, to alpha. And this one here in atomic traps, that's the reference, and that's in the group of Wineland, and this, and that's where they prepare this ion in superposition of two different positions. And these are the examples of what I just said, the destruction of interference of two wave packets in harmonic potentials. These two guys, they received the Nobel Prize in 2012, I think, due to the experimental techniques to deal with the measurement and manipulation of very tiny systems, individual mechanical systems. And okay, so another problem, that's the quantum tunneling of a grounding particle. And so we can have a sort of cubic potential. I put a particle there. Remember the squid. In the squid ring, I have the flux obeying a sort of dissipating equation of motion. And we can tune the external flux in such a way that I can have metastable and bistable configurations, right? And then, this one here, I play, that's one example that I put the particle there, I study the equilibrium configuration, not real-time evolution, but the equilibrium configuration. And since this guy here is not a stable state, we can compute the imaginary part of the energy of the ground state, in this case here, for instance, right? For low temperature behavior, and then we can solve this path integral, or this one here, right? And find the imaginary part of the energy of this metastable configuration. And when we do that, the effect of Euclidean action, as I showed you, is the one of the particle itself, and something which is positive, completely positive. Doesn't really matter what sort of things I have here, square there. So it's positive. So I increase the effective action, and the effective action shows up in the exponent. So I will reduce the probability of tunneling. The probability of tunneling will be reduced by delta. So the decay rate will be given by big gamma. It has nothing to do with the gamma of the destruction of interference. And that's a prefactor, exponential of b divided by h bar, where b is the effective action of a particular path. I will not enter in detail of this thing here, but again, it doesn't really matter what this sort of path is. Its contribution is positive. So you reduce b, you increase b, you reduce this gamma. So we tend to destroy quantum mechanical tunneling. And then, that's the, if I plot, for instance, log gamma minus 1, all minus 1, I have this behavior for very high temperatures. It's a linear term. And linear has to do with the rings. There's thermal activation. fine, physically possible. For very high temperatures, my particle will jump over the barrier, and that's measured in squid rings. The thermal elevation of the flux over the barrier. But then when you start to reduce the temperature, what's going to happen? What happens is that you can perform these, that integral and so on, and find this value here that depend on eta Q naught, where Q naught is the distance under the barrier, right? And for strong damping, we can approximate by this variable. The thing is, look, for this model, all these properties, they do not depend specifically on the coupling. They depend on the overall damping constant, which is phenomenological. That's why experimenters like a lot this sort of thing, this sort of result, because they could really compare that to something which was a phenomenological property. Then, you know, that's what we have. And then if you start to increase damping, you will reduce this probability. Then, you know, you come for very, very strongly damped systems. You tend to be arenas all the time. So classical all the time. You're tending to destroy quantum mechanics as you go on increasing damping. That's all we have here. Now, quartic potential, another very, very important thing for us, especially for us. Now, you know, those who are just, okay, come on, well, where are my qubits? They are coming out, you know, we are very close to them, and but the bistable potential, again, I was biased. I was changing the external flux of the squid ring, and I could bias the system in such a way that I have a bistable potential. Then, you know, we can play with this sort of quartic potential. And in this quartic potential, let us try to play with these two lowest line energy states, separated by h bar omega naught from this first excited state, right? So it's a double, it's a doublet here. And then we have right, left, this linear combination, and symmetric, anti-symmetric combination of psi right, psi left, and there is this energy splitting, depends on the overlap, and it's very small, of course, it's exponentially small. This delta is exponentially small. Delta zero is exactly the split here. Then we can say that what happens if I prepare my system here? Coherently. It will oscillate coherently between right and left. So, nice. I can start to think about going, you know, further and trying to make a, you know, a sort of transformation of this Hamiltonian. Let's try to truncate that only for the two lines, two lowest energy eigenstates. If we do that, we end up with something called the spin-Boson Hamiltonian. And this spin-Boson Hamiltonian is a sort of spin coupled to orthogonal symmetry. And all I have to do is to take the quartic one and try to rewrite that in terms of left and right states. So I can truncate my Hamiltonian just for the subspace of the two lowest line states. That's all I have to do. And now, it turns out that the equation of motion for the average value of sigma x, sigma z, and so on, they obey exactly something like the block equations. Let's take epsilon zero. Epsilon is just a breaking that degeneracy. So if they are completely degenerate, that's what I have. So what we have is the this relaxation time and the dephasing time. And that's something that we can borrow from NMR. And you can see that it's P of t, which is the average value of SZ, is given by this expression. So you see, it is damped by T2. And so that's the dephasing. That's the way you lose coherence when you tunnel from one side to the other. So this SZ starts to jump from one side to the other, plus, minus, plus, minus, plus, minus, plus, start to relax. And it relaxes actually because of this decoherence time. Right? So that's the perturbation theory for the spin boson model. You can show that that's the expression for T1 and T2. So the origin of this guy is unique. It's not like in NMR. In NMR you have the spin lattice relaxation and the spin-spin interaction that will give you the T2. In this case, they have the same origin, the same environment. And in general, what we have is that this T2 is higher than this 2T1 is higher than T2. Okay. One thing that is very nice about the system, the spin boson, is the phase diagram that we have. The dynamics of the system is very rich, depending on the parameters that we have. Let me define this dimension as damping. Eta Q naught squared. Q naught is the distance between the two minimum. 2 pi h bar. And there is this sort of randomized splitting. The randomized splitting is given by this expression. The splitting divided by the cutoff, and this parameter here that has to do. And then we have all these regions, A, B, C, etc., that I will analyze here. So alpha, and we normalize splitting, and let's start with A. The region A is the region beyond alpha equals 1. What happens here is the following. For t equals 0 and alpha greater than 1, what happens is that we have full blocking of the state. If I put my particle on one side of the barrier, it will stay there, completely blocked. There is no way it will go to the other side and come back. Right? That's the result you can get from the solutions of the, you take the double pathing curve for this case here, which is quite messy and so on and so forth. But that's the result. It's quite interesting. And the second one is the high temperature. And for high temperature, this B region, what happens is that we have a complete exponential decay of my spin. So I put the particle on one side of the barrier, and it just relaxes to part half here, half there, exponentially, and that's what happens. So that's not very interesting for us. Now, what about the region of B and C? B and C again. This guy is once again exponential again. And, so we destroy completely the coherence between one well and the other. Now, it's a nice split. T equals 0 and alpha between 0 and half. We are here. This D region, what we have is a sort of dependence that has two parts, a coherent and an incoherent. So this part here, what we have here, Y has a time dependence with this effective splitting, then we have oscillation here. That's some oscillation and then the damping, and that's completely coherent. But this thing here is the important one. Right? So I can have some sort of oscillations. Someone asked me yesterday about what happens if I turn on the coupling with the environment. I said, well, that's exactly what we're going to study, and that's the result. Really, we have some regions when we have the spin boson model that we still have damping, destruction of coherence, but with oscillations. So, and that's exactly, and that's exactly the sort of behavior that you want if you want to use any sort of these guys as a qubit, because you want to have some oscillations before, we within within which we can perform some sort of operations in the system. So that's one thing that we have. So oscillatory decay, and coherent relaxation, and now, 10. Okay, I was telling you about all these applications. Now, I told you about the buffer oscillators. With questions or without questions? Without questions. Thank you. That's enough. Then we have the following now. I will jump to a different model. So, in a way, I told you about something that I claimed it was completely general, but of course, there are systems that we have to be very careful, and they do not obey exactly that picture of oscillators that I used before. Not fully. And I'll give you one example of it, which is the question I call the collision model. And what we have is a particle, just a massive particle in 1D, and this guy here is coupled with 3 particles in 1D, and coupling is just a sort of contact potential. Right? That's the only coupling that we have. That's the scattering of the particle, of these particles of the environment by the external world. If we do that, make this transformation, this unitary transformation given by that, and I will just change this Bj. I think change all these k's by k plus q, and then in the end, what we have is that this transformed Hamiltonian is given by something like this. So it's a set of oscillators. Now, no oscillators, but it's a set of particles now filling the particle, the potential provided by the external particle, and they are coupled in a sort of minimal way with the full momentum of the environment particles. If we do that, and we can write that in a sort of second quantized way, either for fermionic or bosonic particles. So I have a set of non-interacting fermions or bosons as my environment. And in this way here, that's the sort of Hamiltonian that we have. And this J, the coupling, is given by the sort of matrix element of the total momentum of the environment. And if we do that, of course, I will not, we can reproduce all these steps within the path integral formulation if I write a sort of coherent state representation for my creation and destruction operators. If we do that, it's funny, but what we have here is something very similar to what we had before, and again quadratic, but now this gamma of R and gamma I, these guys now depend on the thermal numbers. Right? So these are temperature dependent. The damping now becomes temperature dependent, because the damping I showed you so far is completely temperature independent. But in this model, we start to have this clear dependence on temperature. Okay, so that's the expression that we have, gamma, and that's a sort of time-dependent relaxation, time-dependent diffusion constants, and so if we take the sort of contact potential delta function, we have these expressions here for the gamma of which is temperature dependent. But mind you, again, in order to get these results, I used a harmonic approximation. It is harmonic approximation. Doesn't give us the correct result. For bosons, we have this gamma of t as the sort of dependence, and for fermions, what we have is that we have the at T=0, we still have a sort of finite depth, which is not true. If we take a much more refined approach to that, using a renormalization group perturbation theory for the 1D fermionic path, we end up with something like T⁴ for gamma. And that's what we have in this case. And so gamma goes to 0, and in the case of the mobility of the particle is infinite in this case. So it's not the so the Bath oscillators or the Gaussian approximation for more general system. Although the Bath oscillator is quite general, it's not, of course, the most general thing there is. Then we can start to have other approaches to it, and just a very similar model to this model I just showed you is the following. Let's take a sort of field theoretical model, scalar field. A scalar field in the potential like a 5⁴, for instance. And so what we have, we either have some sort of constant solutions in this configuration or constant configuration up there, or you have a sort of solid interpolating between one minimum and the other minimum of this potential here. And so when you have that, something much more messy, and so we can make the expansion of my continuous variable in terms of this the center of the solid, and can quantize the system here, and in the end, the model that we have is something very similar to the one that we had before. So the guys couple in a sort of minimal way with total momentum of the environment, and that's the total momentum of the environment, and it has to do with the matrix element of the momentum operator, right? So, and this sort of approach is very useful if we have any sort of localized topological excitation in the material system. And we want like the vortex that I showed you yesterday, right? And we can apply something like this. And so we have many other models. There is also a choice for the spin-back model, and in a sense it's a bit different from the Bath oscillators. And but still, what we address today is quite general in terms of this the application of the Bath oscillators. So we have made progress trying in understanding tunneling by coherent tunneling, decay by quantum tunneling, and decoherence of wave packets and all that for dissipated systems. And until, so see you tomorrow, then we'll start to analyze realistic results. I will show you many real experimental results related to the theory I just showed you today. So thank you very much.
Thank you. Do we have questions? There's one right there.
In the down harmonic oscillator, so in the Gaussian case, can't we solve the dynamic exactly? Do we need to use the path integral formulations to do that?
Sorry, in what case? This
No, in the previous case.
previous case, yes.
Yes.
Gaussian approximation, yes, it's still there, exactly. Oh, sorry. Oh, sorry. Okay. Yes.
But do we need to use all this path integral
No,
formulas?
you don't need it.
Okay,
You don't
like-
need it. But mind you, usually people, it's a sort of natural question. Why all these machinery? Why don't you use Lindblad? Because Lindblad requires many approximations between the system and the environment, the sort of coupling that you have. For instance, the state of the system will always be decoupled, or the environment will always be decoupled from the system. In our case, I do not assume anything like that.
But even even without Lindblad, if I have a quadratic coupling between my system and the environment, can't I always diagonalize the Hamiltonian?
Yes, yes, you're right. I can use I can play with the operators, for instance, and use the equation of motion. Absolutely, yes, you can do that. In this case, you can do that. But now, for the wave packet, the harmonic oscillator, yes. But now, what about the decay by quantum tunneling? How can you solve that? How can you solve tunneling problems within the Heisenberg formulation? You can do that for the example you just given, but not for the quantum mechanics, for the decay by quantum tunneling, or even the coherent tunneling.
Okay.
So these are very tricky issues. And sometimes even if you can show what happens to the destruction of coherence from one side to the other by stable potential, what about the randomization of the splitting? It's there. You can read, depending on the system, you can reach regions of this effective damping where you have complete block. You will reduce to zero your splitting. So there is no coherence from one side to the other. You put it there, it will be there forever. And so one has to be very careful when trying to use master equations for these sort of problems. Because if you take, for instance, this very model of harmonic oscillators and try to use that super propagator in a sort of infinitesimal time evolution, we can reduce master equations. They are far from being Lindblad. Nothing to do with Lindblad. That's the thing. But I agree that many people are in favor of Lindblad and use Lindblad all the time and many other models. No problem against it. The thing is, these systems, okay, they are very weakly coupled systems, right? And what we're talking about is something else, something more general. Of course, I can play with that and show that what is the condition to jump from the baffled oscillator's expressions to the rotating wave. I can tell you, it's extremely low damping. That's very, very, very underdamped systems. Otherwise,
Thanks. If I can ask another question. Oh. Is for the quartic potential, is the only thing we can do is truncation?
Yep.
There's nothing else we can do, like I don't know, power expansion or randomization.
Well, the thing is, okay, why you want to, yes, you can always try to, you can use that. You can use the full quartic potential, and okay, it depends on what you want to answer. What you want to extract from this formulation, and what you want to measure from that system. Because then, you are in a regime where, for instance, all this structure of the high energy levels, very close to the top of the barrier, they show up. Really, if you want to address things that go from the very low temperature to the very high one, even making the crossover from the pure quantum regime to the thermal activation, entirely, you have to use the full potential. But then you have techniques to do that.
Thank you for the lecture. So at the beginning of the presentation, the particle that you are using, the harmonic oscillator, could be treated as a classical one. But I'm not familiar with the spin boson model, so it can be silly, but it can be interpreted as a qubit. And when you do the Feynman-Vallon theory and treatment, how could you extract the equations of motion as you do in the beginning? I don't know if I understand very well this part, because in the beginning you just do
The
Lagrange.
block equations.
Yeah,
Oh,
exactly.
yeah. That's basically perturbation theory, and then you perform the averages of all these, because you have sigma z and sigma x in the Hamiltonian of the spin boson, and then you try to write that. In the end, you write Heisenberg equation of motion, and you end up with these block equations. So that's the idea to use block equations was really to make a sort of analogy with something else that you know that you used it, right? The sort of block equation for NMR, for instance. But now, in order to have all that phase diagram, you do not use block equations. You go to the Feynman and you operate and you perform all those path integrals, and mind you, they are quite tough because you have this sort of hopping paths from one side to the other, and it's a bit messy. But that's again brute force, and you can solve that within some reasonable approximation, and also numerically you can do that. But so the block equations was only to show you some sort of analogy. It's something that you already know. Sorry to. So thanks to asking the question.
Thank you.
All right, any more questions? Well, if not, let's thank Amir again.